Hello, I'm Marco Colavincenzo, and this is my Chemistry in the News assignment on the article Breakthrough in Hydrogen Research. Now, for some background, hydrogen has three isotopes: protium, hydrogen-1, which has an isotopic abundance of 99.9885%, deuterium, hydrogen-2, which has an isotopic abundance of 0.0115%, and tritium, hydrogen-3, which is a radioisotope of hydrogen that has an isotopic abundance that is around 10 to the negative 18th of protium's isotopic abundance. Now, while that may make it sound as if there's very little deuterium and tritium, as hydrogen is the most abundant atom in the universe, even such a small isotopic abundance of deuterium is relatively common. For example, the ocean alone contains tons, as in the metric unit, of deuterium. Now, for the uses of these isotopes, deuterium has pharmaceutical uses, largely to improve the pharmacokinetic properties of certain drugs, such as paroxetine, which is a drug used to treat depression. Pharmacokinetic properties just refers to the speed of a drug's effectiveness. So a deuterated drug, which is one where the protium is replaced with deuterium, can often be more effective quickly than one with protium. Now, deuterium and tritium are also what are used for current nuclear fusion reaction trials. When heated until they become plasma and lose their electrons, with pressure they fuse into helium, with the extra neutron being released and energized, which when done on a large scale provides an extreme amount of energy as heat, making nuclear fusion extremely energy efficient. 4 times as efficient as nuclear fission and up to 4 million times as efficient as burning oil or coal for the energy generated per kilogram of fuel used. If nuclear fusion were to ever be used on a wide scale, having a consistent supply chain processing these isotopes would be vital. And this leads us to the problem. While there are many uses for hydrogen isotopes and a relatively vast abundance of them, the process for separating and collecting them are inefficient and consume large amounts of energy. These isotopes must also be very pure for the uses that they are most commonly wanted for, but their similar physical properties make it difficult to extract one without extracting the other, negatively affecting the purity. For example, if you want to extract just deuterium, it's often very difficult to not also extract protium. Now, for years we've known it should be possible to use a porous metal organic framework to extract the isotopes, but the issue is that it would have to occur at negative 200 degrees Celsius. Now, for context, a metal organic framework is a crystalline compound consisting of metal ions. So while this process would be possible, it would be expensive and inefficient, especially on an industrial scale. And that is where the main article comes in, as it largely focuses on new discoveries about these metal organic frameworks. So these porous frameworks separate the isotopes through adsorption. Adsorption happens when atoms, ions, or molecules of gases or liquids adhere or stick to solid surfaces, in this case, the porous metals. Now, this diagram shows how this works, with some gases being stored in the framework to be collected while other parts exit out. Theoretically, this is how we'd hope it would work with the hydrogen isotopes. You can imagine the yellow being deuterium, the orange being tritium, and the green being protium. It would collect the isotopes we want inside of the framework while releasing the ones that we don't care about. This recent research has helped further our understanding of how the framework environment affects the selectivity of the bonding, which allows us to know more about why one of the isotopes might be more likely to stick than the others. We can now see the specific influences atoms have in these frameworks on absorption, which allows scientists to optimize the materials used to allow the high selectivity needed for these processes to occur at room temperature rather than negative 200 degrees Celsius. This is a big deal, as it would allow it to be much more efficient energy and cost-wise to collect these isotopes. There's currently a few $1 million being put into the research on this topic, making it an exciting development that may help industries in the future. Now, for the conclusion. Deuterated drugs are very useful and are not uncommonly used. Having an easier time collecting deuterium can allow more effective drugs to become more commonplace. This development can also help accelerate the development and research of fusion reactions, as more access to the fuel needed means that more trials can take place and more understanding can be gleaned quicker. Additionally, while fusion is currently not a usable energy source on a large scale, if we ever get to that point where it can be, this would allow a more consistent flow of these isotopes as fuel, which would be vital to providing clean energy efficiently and quickly. As for next steps, scientists should just keep doing what has been being done, continuing the research of these materials to make them more effective, deepening our understanding of them, and getting them working on a large scale. Thank you for watching.